Hello students. Uh, in this video, I would like to teach one more important question, and this question is repeatedly asked in your DSP examination, and that is find out the frequency response and of a given function. He is asking the question. The particular examination asking the question is that find the frequency response of the given function and determine the sketch and magnitude and phase response of the given function. Okay, so now I would like to with explain with this one example, that is so here uh, find the frequency response of the given function and also plot the magnitude phase response of the function, and that is given by y of n is equal to 1 by 2 of x of n plus x of n minus 2. So this is our question. Okay, so we need to find the frequency response of the given function and also plot the magnitude and phase response of this given function. Okay, so for this case the solution is that the given function, what is our given function? Y of n is equal to 1 by 2, okay, into x of n plus x of n minus 2. So in order to determine the frequency response, okay, so before that we should know about the discrete time Fourier transform formula. Okay, so for that a little bit I want to give a little bit discussion about the discrete time Fourier transform. Okay, see, this is a note. Okay, uh, so discrete Fourier transform pair. This is discrete time Fourier transform pair, which is given by x of e to the power of j omega, which is equal to sigma n is equal to minus infinity to infinity x of n into e to the power of minus j omega n. Okay, and where small x of n is given by 1 by 2 pi integral of minus pi to pi. Okay, x of e to the power of j omega into e to the power of j omega into d omega. Okay, so where the x of e to the power of j omega is the discrete Fourier transform of x of n, dft. Okay, so dtft of x of n, where the small x of n is refers to inverse discrete Fourier transform, inverse discrete time Fourier transform of x to the power of e to the power of j omega. Okay, so these are the formulas which are applicable, discrete time Fourier transform pair. Okay, so this is very important. Now by using these two formulas, now we would like to find out the frequency response. Okay, now we will see how to solve this one. Okay, okay, now in order to determine the frequency response of the system, okay, what should we do? Okay, so generally the frequency response of the system, which can be expressed in terms of h of e to the power of j omega, h of e to the power of j omega. Okay, and the quantity, this h of e to the power of j omega is referred as the frequency response of the system. Frequency response of the system. Okay, so here h of e to the power of j omega, which can be expressed as sigma k is equal to minus infinity to infinity h of k into e to the power of minus j omega n. This is discussed in just okay. This is discrete time Fourier transform of h of n. Okay, impulse response. Okay, so here the frequency response of the system is a discrete time Fourier transform of the impulse response h of n of the system. Okay, from that the frequency response h of e to the power of j omega, which is a complex valued function, and this is a complex valued function. Okay, and it can be expressed in polar form. When it can be expressed in polar form. Okay, and that is given by, so h of e to the power of j omega, which is expressed in terms of polar form, that is h of e to the power of j omega, okay, in modulus of e to j omega, and e to the power of j theta omega, e to the power of j theta omega. So where the modulus of h of e to the power of j omega, this one, modulus of h of e to the j omega, which indicates the magnitude response, which indicates the magnitude response. Okay, and the theta omega. Okay, so the theta omega, so the theta omega, which is can be expressed theta omega equal to phase of h of e to the power of j omega, so which indicates the phase response of the system, phase response of the system. Okay, one thing you should remember, this magnitude response, okay, which is an even function, okay, which is an even function of omega, even function of omega. Okay, whereas the phase response, which is an odd function of omega, odd function of omega. Okay, so the what is the even function? So the modulus of h of e to the power of j omega, okay, so which is equivalent to modulus of h of e to the power of minus j omega. And what is odd function? Odd function is nothing but theta of omega. So basically, theta omega is, which represents the phase response. So I am expressing in terms of theta omega. Theta omega is equal to, is expressing modulus of theta of omega. Sorry, theta of omega, which is equivalent to modulus of theta. Sorry, theta omega is equal to minus of theta of minus omega. Okay, this is a an odd function of omega. Okay, so this is a small introduction about it. So in order to find out the frequency response of the system, first of all we need to determine, so h of e to the power of j omega. Okay, so it is in a complex valued function. You need to determine h of e to the power of j omega, and after finding out this h of e to the power of j omega, now you are going to express this h of e to the power of j omega in terms of modulus of e to the power of j omega and e to the power of j theta omega. Okay, so where the modulus of h of e to the power of j omega, which indicates the magnitude response, and theta omega, which that is a phase angle of h of e to the j, which indicates the phase response of the system. Okay, so with this magnitude response and phase response, we can plot the magnitude response of the h of e to the power j omega and the theta of omega. Okay, so this is an introduction part of the frequency response of the system. Now, according to our question, what is our question? So we need to find out the frequency response of the given function, that is y of n is equal to 1 by 2, okay, into x of n plus x of n minus 2. Okay. So in order to determine the frequency response of this function, you should express this function in terms of h of e to the power of j omega, that is equal to y of e to the power of j omega by x of e to the power of j omega. If you can determine this given function in the terms of y of e to the power of j omega by x of e to j omega, then it is equivalent to h of e to the j omega. Then it is nothing but the frequency response of the system. Frequency response of the system. Okay. So for that, you should apply the discrete Fourier transform. Okay, discrete Fourier transform of this given function. Okay, let us say this is equation number 1. Okay, apply discrete Fourier transform of okay, so y of n, which is given by, okay, so y of e to the power of j omega, which is equal to sigma, where our this is in time domain now, so n, okay, n is equal to minus infinity to infinity, y of n into e to the power of minus j omega n. Okay, so what is y of n? Our y of n is nothing but 1 by 2 into x of n plus x of n minus 2. Substitute this one. Okay, so sigma n is equal to minus infinity to infinite. Okay, so 1 by 2 into x of n plus x of n minus 2 into e to the power of minus j omega n. Okay, expand this equation. Okay, and simply by solving we get y of e to the power of j omega and x of e to the power of j omega. Okay, now we will see. Okay, so sigma, this 1 by 2 is a constant, so it is come outside, and the final is, okay, sigma uh, n is equal to minus infinity to infinite. Okay, so this is x of n into e to the power of minus j omega n. Okay, so this is one, and next one sigma n is equal to minus infinity to infinite x of n minus 2 into e to the power of minus j omega n. Okay, so this is one. Okay, now this can be written as 1 by 2. Okay, so this is in the form of again discrete Fourier transform of x of n, so this can be written as x of e to the power of j omega. Okay, but this form is in time shifting property. This form is in time shifting property. With the help of time shifting property, with the help of this time shifting property, okay, so we can simplify this given function. We can simplify this given function. Okay, so before that we should know not about this node. Okay, what is a time shifting property? Okay, if discrete Fourier transform of f of x of n, which is equal to x of e to the power of j omega n, if it is, then okay, the Fourier transform of discrete Fourier transform of x of n minus k, okay, so which equivalent to e to the power of minus j omega k into x of e to the power of j omega. Okay, so this is the property, and this property is nothing but a time shifting property. Time shifting property. Time shifting property of DTFT. Okay, so by using this property, what is our property? This one. Okay, so this is in the form of, say, x of n minus 2, x of n minus 2 now. Okay, so by using this property, okay, now this can be written as, this can be simplified as e to the power of minus j 2 omega, where k is equal to 2. See, where k is equal to 2, by compare this one, x of n minus k, and then this one, and this one is equal to x of into x of e to the power of j omega. Okay, see, this is by taking as x of e to the power of j omega as a common, so x of e to the power of j omega by 2, and what is the rest of function is here? 1 plus e to the power of minus j 2 omega, or e to the power of 2j omega. Okay, so now see, okay, so here y of e to the power of j omega is equal to, y of e to the power of j omega is equal to x of e to the power of j omega by 2 into 1 plus e to the power of minus 2j omega. Okay, in order to find out frequency response, we require it is equal to h of e to the power of j omega, which is equal to y of e to the power of j omega by x of e to the power of j omega. Okay, so this is equivalent to 1 by 2 into 1 plus e to the power of minus 2j omega. Okay, so this is the frequency response of the given function. This is the frequency response of the given function. or given system. Okay. Now this is first portion is completed. Now in order to determine the magnitude response and plot response, what should we do? Okay. So for magnitude response or for plot response, this h of e to the power of j omega. So this h of e to the power of j omega should express into modulus of h of e to the power of j omega into e to the power of j theta omega, where theta omega which is equal to the phase angle of h of e to the power of j omega. Okay, so in order to find this one. Okay, so for that, so what is a obtained frequency response? That is h of e to the power of j omega is equal to 1 by 2 into 1 plus e to the power of minus 2j omega. Okay, and this can be modified as in terms of cos and sine. Okay, so this can be simplified as 1 by 2 into 1 plus cos 2 omega minus j sine 2 omega, j sine 2 omega. Okay, so to plot magnitude response and phase response, we need to determine the modulus of h of j omega for the magnitude response. Okay, and angle of phase response of h of e to the power of j omega. Okay, so for that, so to obtain modulus of h of e to the power of j omega, this can be written as 1 by 2 into, okay, which is square root of, okay, a square plus this b square. Okay, so 1 plus cos 2 omega whole square, okay, plus okay, sine square 2 omega. Okay, now we can what is it? 1 by 2, 1 by 2 into square root of, this can be expressed as 1 plus cos 2 omega whole square. This can be expressed as 1 plus cos square 2 omega plus 2 cos 2 omega, 2 cos 2 omega plus sine square 2 omega. Okay, so this is, so here this is a cos square a plus sine square a, so which is equal to 1. So 1 by 2 into 1 by 2 into, and cos square a. So this can be written as 1 plus cos square 2 omega plus sine square 2 omega. Okay, and plus 2 cos 2 omega. Okay, and now this can be written as 1 by 2 square root of 1 plus, and this becomes, the center equation becomes 1, and plus 2 cos 2 omega. Okay, and which is equal to 1 by 2 square root of 2 plus 2 cos 2 omega. Okay, so this can be written as again, this can further simplify as by taking as a 2 as a common, and this is 1 plus cos 2 omega. Okay, and this is 1 plus cos 2a in the form. 1 plus cos 2a can be expressed as 2 cos square a. Okay, so 1 plus cos 2a is equal to 2 cos square a. Okay, so by using that formula, 1 by 2 is equal to 2 into this is 2 cos square omega. Okay, and this is equal to 1 by 2 into square root of 4 into cos square omega, and this is equal to 1 by 2 into 2 cos omega, and this 2 gets cancelled, and finally we get a cos omega. Okay, so this is a modulus of h of e to the power of j omega. Okay, so this is magnitude response. Okay, now, so I am writing clearly, modulus of h of e to the power of j omega is equal to cos omega. And after that we need to find out phase response. So h of angle of h of e to the power j omega, which is equal to, so which is equivalent to tan inverse of minus b by a, that is equal to tan inverse of minus b by a. So in that our h of e to the frequency response, which is given by the frequency response, that is okay, what is that here, what is the yeah, it can be shown. Yeah, h of e to the power j omega is equal to 1 by 2, which is given by 1 into 1 plus cos 2 omega minus j sine 2 omega. Okay. So tan inverse is equal to, what is the function here? So h of e to the power of j omega, that is given by h of e to the power of j omega is obtained as 1 plus cos 2 omega minus j sine 2 omega by 2. Okay. So here the tan inverse is minus b by a. Sorry, tan inverse of b by a, not minus b by a, tan inverse of b by a. So here the b term is nothing but sine 2 omega minus sine 2 omega by a term is 1 plus cos 2 omega. Okay, this one. And then, so which can be simplified as a tan inverse of, okay. So this minus sine 2 omega can be written as a uh, minus 2 sine omega cos omega. That is sine 2a is equal to sine 2a can be expressed, okay. Sine 2a is equal to 2 sine a cos a. Okay, so 2 sine omega by cos omega. Okay, and this 1 plus cos 2 omega can be written as 2 cos square omega. Okay, so here one cos term and cos omega gets cancelled. Finally, tan inverse of finally the remaining term is this 2 gets also cancelled. So finally it is having minus tan omega. So tan inverse of minus tan omega is nothing but minus omega. So this is about phase response of e to the power j omega. Okay, this is phase response. Now, by choosing the different values in terms of omega, now we can plot for the magnitude response and the phase response of the given system function. Okay, how to find this one? So this is very simple. Okay, so once you determine these values of magnitude and phase response, okay, so here we can take omega, okay, and h of e to the power of j omega, okay, and which is equal to 1 plus cos 2 omega minus j sine 2 omega by 2, okay, and modulus of h of e to the power of j omega, and which is nothing but cos omega, okay, and the phase response of h of e to the power of j omega, which is equal to minus omega. Okay, so this is the portion. So here's omega. So though we know that modulus of h of e to the power of j omega is an even function or a symmetric function, and the phase response of h of e to the j omega is a odd function, or we can say that antisymmetric function with a period of 2 pi in omega. Okay, so in order to find, we need to consider over the interval of this omega, we can consider in the range of 0 to plus less than equal to omega less than equal to pi. Okay, by because within this. Okay, so I'm randomly selecting the omega value is 0 and pi by 6 and pi by 4. Random I am taking pi by 3, okay, and pi by 2, 2 pi by 3, okay, and 3 pi by 4 and pi. Okay, I'm taking these values only. Okay, so by substituting omega is 0 in this h of e to the power of j omega, okay, its value equal to 1. Okay, and modulus of h of e to the j omega is also its value is equal to 1. Okay, so omega is 0, so there is a 0. Like that way, so when you substitute omega is equal to pi by 6 and substitute this omega in this h of e to the omega, we get 0.812 its value. So modulus of e to the j omega, so its value is equal to 0.812 only. Okay, and this value is minus omega, so here's omega is pi by 6 and minus omega, so its value is equal to minus pi by 6. So when you substitute pi by 4, its value is equal to 0.707, and it's 0.707, its value is 0.707, and its value is equal to minus pi by 4. Okay, and um, so actually this value we need not to consider. This is frequency response. We need not to consider. So we get wrong values here. Okay, okay. So we consider only this value, magnitude response, and this one. Okay. So if we substitute, we're getting another values here. No problem at all. So pi by 3. If we substitute pi by 3, its value is equal to 0.5, and its value is equal to minus pi by 3. Okay. When we substitute pi by 2 cos 90, its value is equal to 0, and its value is equal to pi by 2. 2 pi by 3, its value is equal to 0.5, and this is pi by 3. When it's 3 pi by 4, its value is equal to 0.707, and its value is equal to pi by 4. When it is cos pi, its value is equal to 1, and this value is equal to 0. Okay, so these are the values. So once you find the you determine the table, next you need to draw the magnitude response. Okay, so the magnitude response. So the magnitude response plot for this one. So here you take. So this is a magnitude. This axis is magnitude axis, and this axis is omega axis. So 0, pi by 6, pi by 4, and pi by 3, pi by 2, and 2 pi by 3, and 3 pi by 4. So pi. Okay. So initially for 0, its value is equal to 1. So its value is equal to 1, 1. Okay. And for pi by 2, its value is equal to 0. For pi by 2, its value is equal to 0. So here also 0. For pi, its value is equal to 1. So its value is equal to 1. For pi by 6, its value is equal to nearly 0.812. Somewhere it is existed like that. For pi by 4, its value is equal to 1 by root 2 something. Okay. So 0.707. Okay. This one. Again, for 3 pi by 4, its value is equal to 3, basically symmetric value, so its value is equal to again 0.75. For pi by 3, 2 pi by 3, its value is equal to 0.5, so 0.5, 0.5. So the plot curve is here like this. So this is the plot. Sorry, I'm not drawing properly. So this way. So this is the magnitude plot. Similarly, for phase plot. For phase plot, so again, you need to consider omega is one of the axis, and phase is another axis. Okay, so this is pi by 2, and this one is the minus pi by 2. So this is 0. Okay, so again the axis is same. So pi by 6, and pi by 4, and pi by 3, and pi by 2, and 2 pi by 3, and 3 pi by 4, and pi. Okay, so here for omega 0, its value is 0. Omega is 0, its value is equal to 0. Okay, 0. For pi by 6, its value is equal to minus pi by 6. Okay, it is a range of pi by 2, pi by 2 now. So its range is minus pi by 6. So somewhere, okay, it is existed like that. For pi by 4, its value is equal to minus pi by 4. Okay. For pi by 3, its value is equal to minus pi by 3. For pi by 2, its value is equal to minus pi by 2. Okay. For 2 pi by 3, its value is equal to pi by 3. Its value is equal to pi by 3. Okay. And for 3 pi by 4, its value is equal to pi by 4. And for pi, its value is equal to 0. So by connecting all the samples, sorry. So, so this is a phase response of the given function. Okay, like this way, we need to find the frequency response and the magnitude response and the phase response. Okay, thank you.